Here are the solutions to a logarithms test for the grade 12 advanced functions course. Section 1 is true or false. Question 1 says log of x plus y is equal to log x plus log y. I know that's false. The product rule of logarithms tells me that if I'm adding logs with the same base, I know that would be equal to a single logarithm with that same base with the arguments x and y being multiplied, not added. So I know it is not equal to log of x plus y. It should be equal to log of x times y. So this statement was false. If I look at number 2, it says you can rewrite log 20 minus log 5 as log 15. This is really similar to number 1, but this one involves the quotient rule of logarithms. I know that log 20 minus log 5, based on the quotient rule of logarithms, that should be equal to a single logarithm with the same base of 10, but the arguments need to be divided. 20 divided by 5 is 4, so this should be equal to log of 4, not log of 15. So number 2 is false as well. Number 3, you can write log x divided by log y as log of x divided by y. That's false as well. Based on the change of base formula, I know that log x divided by log y should be equal to log base y of x. And another reason I know this is false is because log of x divided by y, based on the quotient rule of logarithms, is equal to log x minus log y. So for both of those reasons, I can see that this statement is false. So number 3, false as well. But if we look at number 4, finally we have a true statement. It says 4 times log x equals log of x to the 4. That's the power rule of logarithms. You can take the exponent of the argument of a logarithm and rewrite it as the coefficient of that log. So number 4 is true. And keep in mind, for these true and false questions, you could have picked test values for x and y and substituted in and seen if they were equal to each other or not, and then you would have known if this statement was true or false. Let's move on to section 2, which is multiple choice. Number 5 says evaluate log of 1. Let's do that without a calculator, of course. I know if I don't see a base of the logarithm, the base is 10. So this expression, what does that mean? It means 10 to what exponent equals 1? Well, I know 10 to the 0 equals 1, so log 1 must be 0. Number 6 says to rewrite log base 4 of 52 equals y in exponential form. In exponential form, this expression would be 4 to the power of y equals 52. Right? A logarithmic expression gives you the exponent y that goes on the base of the log 4 to get the argument 52. And that's what this expression says. It says 4 to the y equals 52. So the answer, A. Number 7, evaluate log base 5 of root 25. It would help if I rewrite the argument of the logarithm as a power of base 5, since that's the base of the logarithm. So I'm going to change that 25 into a 5 squared. So I've got log base 5 of 5 squared to the half. Right, a square root symbol just means an exponent of a half. And now when we have an exponent on top of an exponent, we can multiply them together. 2 times a half is 1. So this really just equals log base 5 of 5. And now this expression just means 5 to what exponent equals 5. 5 to the 1 equals 5, so the answer is B. Number 8, evaluate log base 3 of negative 9. I know the value of this does not exist because the argument of a logarithm has to be greater than 0. So for that reason, it does not exist. And I'll make a note. Argument has to be greater than 0. All right, that's it for the multiple choice. Let's move on to the next question where we have to simplify some expressions. Question 9 says, write as a single logarithm and then evaluate. Round to 2 decimal places if necessary. So for A, I notice I have 2 logarithms that have the same base being subtracted. So I can write those as a single logarithm by keeping the same base and dividing the arguments. 80 divided by 10. So this equals log base 2, 80 divided by 10 is 8. And now this expression just means what exponent goes on 2 to equal 8. I know 2 cubed is 8, so the answer to this is 3. So there would be 2 marks here. One for writing it as a single log, and the next for evaluating. Part B. If I'm going to combine these three logarithms into a single logarithm, I need to make sure all of their coefficients are 1 first before using the product and quotient rules of log. So this too, I need to use the power rule of logarithms and write it as the exponent on the argument. So I'll do that in my first step. So log base 3 of 4 plus log base 3 of 4 squared minus log base 3 of 8. The first two logarithms have the same base and are being added. So I can combine those together by keeping the same base and multiplying their arguments. I have 4 times 16. That's 64. And now I have two logs with the same base being subtracted using the quotient rule of logarithms. I can write them as a single logarithm by dividing the arguments. 64 divided by 8. And 64 divided by 8 is, of course, 8. And now I'm trying to figure out what exponent goes on 3 to get 8. It's going to be bigger than 1, but less than 2. You'll have to use your calculator to get an approximate value for this. And the question, remember, said to round this to 2 decimal places. That would be approximately 1.89. Let's move on to C. If I want to combine these two expressions into a single logarithm, I need to use the change of base formula. The change of base formula tells me that this would equal log base 8 of 20. Notice the bases of 9 on both of those logarithms don't appear anywhere in this expression. All that mattered was that they were the same base, and then I was allowed to use the change of base formula. And now if I want log base 8 of 20, what exponent goes on 8 to get to 20? Well, it's going to be 1 point something. Use your calculator to get an approximate value. And it's 1.44. Moving on to D. I have two logs being subtracted that both have the same base, right? Those are both the common logarithm. Their bases are 10. So I can write them as a single logarithm by keeping the base of 10 and dividing their arguments. But then I can simplify that argument. In the numerator, I have a difference of squares. It's an x squared minus a 2 squared. So I could rewrite that as x minus 2 times x plus 2. And in the denominator, I have a quadratic trinomial. I could do sum and product factoring. I could find numbers that have a product of 8 and a sum of negative 6. The numbers that satisfy that product and sum are negative 2 and negative 4. So I know this quadratic would factor to x minus 2 times x minus 4. The x minus 2's would cancel out as long as x doesn't equal 2. And my expression would be equal to log of x plus 2 over x minus 4. There's nothing to evaluate for that expression because we don't know the value of x. So notice for each of those questions, we did two things. We wrote them each as a single logarithm, and then also got the value of that logarithm. Except for in part D, couldn't find the value because we had a variable that we didn't know the value of. All right, let's move on to question 10. It says, is it possible to write 20 as a base 3 power? If so, write it. If not, explain why not. Now, this question's good because you should know that it's possible to write any positive number as a power with the base of any other positive number. So it is definitely possible to write 20 as a base 3 power. I can use the logarithm rule that tells me that a to the log base a of b equals b. So if I want a base 3 power to equal 20, I would just say, okay, I'll say yes, it's possible. As a base 3 power, okay, I'll make the base of the power 3, and the exponent would become log base 3 of 20. If we evaluate this, it would equal 20 exactly. Why does that make sense? Well, this, if you understand logarithms, means the exponent that goes on 3 to get 20. So whatever that value is, right, it's 2 point something. When we put it as the exponent on 3, we of course get 20. Moving on to question 11. We just have two questions left on this test. We have to solve some exponential equations, and then question 12, we have to solve some log equations. So back up to 11, let's solve these four exponential equations. It says, show appropriate methods and round to 3 decimal places where necessary. This first exponential equation, the most appropriate method, since I have a power equal to a power, I would try and rewrite those powers with the same base. I could rewrite this power base 2 and this power base 8. I could write them both as base 2 powers. So I'll leave 2 to the x minus 1, and I see that I could rewrite 8 as 2 cubed. When you have a power raised to an exponent raised to another exponent, we multiply those exponents together. So we will do 3 multiplied by 2x plus 3. Remember to multiply by the 2x and the 3, which gives us 6x plus 9. And now that we have power equal power where the bases are the same, the only way this could be true is if the exponents were equal. So set the exponents equal to each other and solve. So x minus 1 would have to be equal to 6x plus 9. I'll bring the constant terms to the left and the variable terms to the right. I'll have negative 10 equals 5x. Divide both sides by 5. I get x equals negative 2. And don't forget, you can check that answer in the original equation. Make sure it makes left side equal right side. Part B, I notice I just have one term with a variable, and that variable is in the exponent. So I can just convert this into logarithmic form and be able to easily solve for the variable. In logarithmic form, I know the exponent is the answer, so x plus 3 is the answer to the logarithm. And the logarithm has two parts, a base and an argument. The base of the power becomes the base of the logarithm. So I would have log base 21 of 14. And to isolate the x, all I have to do is subtract the 3 to the other side. So log base 21 of 14 minus 3. That would be the exact value. I can evaluate that on my calculator to get an approximate value. I get about negative 2.133. Let's move on to part C. This time, both powers have a variable in the exponent. So I would try and rewrite these powers with the same base, but 3 and 5, it's not easy to rewrite those as powers with the same base. So instead, I'll use a different strategy. I'll take the common logarithm of both sides of this equation. And now I'll use the power rule of logarithms to take both of those exponents of the arguments and write them as the coefficients of the logarithms. Now I'll expand both sides. On the left, I'll do x times log 3 plus 5 times log 3, and on the right, 2x times log 5 minus 1 times log 5. Now I notice I have two terms with a variable. I'm going to want to get those on the same side of the equation. And two constant terms, I'm going to want to get those on the same side of the equation. So I'll bring the constant terms to the left and the variable terms to the right. And now I'll do a bit of simplifying and rearranging. On the left side of the equation, I noticed that I could combine these two logarithms using the product rule, but before I do that, I would have to move this coefficient up as the exponent on the argument. So it would become log of 3 to the 5, and 3 to the 5 is 243, plus log 5. And I'm going to continue on the left side a little bit, actually. Now I can combine these two logs that are being added with the same base by keeping the base the same, keep the base 10, and multiply the arguments. 243 times 5 is 1215. Now on the right side of the equation, you should notice that both terms have an x. So you should common factor out an x from both terms. When I divide both of these terms by the x I took out, I get 2 log 5 minus log 3. And let me actually combine these two logarithmic expressions. I would first have to move this 2 up as the exponent on the 5 to make it 5 squared, which is 25. And then because these logs are being subtracted, I could write them as a single log by dividing their argument. So they would become log of 25 over 3. And now to isolate the x, I just have to divide both sides by log of 25 over 3. So I'd have log of 1215 divided by log of 25 over 3 equals x. I might as well combine those two logs into a single logarithm using the change of base formula, which tells me those would equal log base 25 over 3 of 1215. That's the exact answer to this question. If we want an approximate answer, we could use a calculator to evaluate that. And I get about 3.35. Moving on to part D. Here I actually have an exponential equation of quadratic form. Let me rewrite this 5 to the power of 2x as a 5 to the x squared so you can more clearly see that quadratic form. Now if I use a let statement, let k equal 5 to the x, the equation becomes k squared plus 8k minus 20 equals 0. Now it's just a normal trinomial quadratic with a leading coefficient of 1. So we would just find numbers that have a product of negative 20 and a sum of 8. The numbers that satisfy that product and sum are 10 and negative 2. So I know that quadratic would factor to k plus 10 times k minus 2. So the answers to that equation are k equals negative 10 and k equals 2. But remember, those k's are actually 5 to the power of x. So let me resubstitute back in 5 to the power of x for each of those k's. And now I'll try and solve both of those equations by converting both of those exponential equations into logarithmic equations. I'll focus on the first one. I can find the exponent, x, by doing log base 5 of negative 10. And now I see there's going to be no real solution to this because the argument of a logarithm has to be greater than 0. Right? And that should make sense. There's no exponent we can put on 5 to make it become negative. But how about this equation? 5 to the power of x equals 2. So what exponent goes on 5 to get 2? I can use a logarithm to find that exponent by doing log base 5 of 2. My calculator tells me that that is approximately 0.431. So that is the only real answer to this equation. So we've solved all 4 exponential equations. Let's move on to the last question of the test where we have to solve some logarithmic equations. Question number 12 says solve the following log equations, round to 3 decimal places, and check for extraneous roots. Make sure the answers you get actually satisfy the original equation. There is a chance when solving log equations you get an answer that makes either side of the original equation be undefined by making the argument of any of the log expressions in the equation be less than or equal to 0. So we'll have to make sure to check that. The first equation. First of all, I'm going to rewrite that square root as a rational exponent. That's equal to an exponent of a half. And now I'll use the power rule of logarithms, which tells me I can take that exponent, write it as the coefficient of the log. And now if I multiply both sides of this equation by 2, I notice both of these fractions are going to be gone. So all I'm left with is log of x squared minus 3x equals 1. And now I'll convert this into exponential form. On the left, we have the common logarithm where the base is 10. So what this means, it means that 10 to the power of 1 is equal to the argument. So that's what I'll write. I'll write 10 to the power of 1 equals x squared minus 3x. Now this is just a quadratic equation to solve. So I'll set it to 0 by moving the 10 to the right. And now I'll find the numbers that have a product of negative 10 and a sum of negative 3. The numbers that satisfy that product and sum are negative 5 and 2. So it would factor to x minus 5 times x plus 2. So the solutions to this equation are x equals 5 and x equals negative 2. But we have to check, are either of those answers extraneous? Do either of those answers make the original log expression undefined? If I were to sub my answer of 5 into the left and right side of this, let me just do a quick check. If I subbed 5 in for both of these x's, underneath the square root would become 10. So I would have log of root 10, I'll write that as 10 to the half. And remember that can move down. So I've got a half log 10, and log 10 is just 1. So a half times 1 is a half. And that is the same as the right side of the equation. So 5 is a correct answer. Let me also check my answer of negative 2. If I were to sub negative 2 in for those x's, it would make this become 10 as well. So on the left side, I would have log of 10 to the half, which is the same as we had before. So that's a half log 10, which is just a half, which is the same as the right side of the equation. So that is just verified that both x equals 5 and x equals negative 2 are both solutions to the original equation. Let's move on to part B. I have two logs with the same base being added, so I'm going to write those as a single log by keeping the same base, keep the base of 10, and multiply their arguments, x plus 2 times x minus 1. And now I'm going to convert this to exponential form. The base of the log is 10 in exponential form. I would write that 10 to the power of 1 is equal to the argument. And the argument, if I were to expand it, would be x squared plus x minus 2. It's once again a quadratic to solve. I'll set it to 0 by moving the 10 to the other side and collecting it with the negative 2. I get negative 12. I could now factor this quadratic trinomial by finding the numbers that multiply to negative 12 and add to 1. The numbers that work are 4 and negative 3. So I know this factors to x plus 4 times x minus 3. So the solutions to that equation are x equals negative 4 and x equals 3. Let me check and make sure that neither of those answers are extraneous by subbing them into the original equation. I can already see that negative 4 is going to be an extraneous solution because if I sub it in for x into either of those log expressions, it makes both of the arguments become negative. And log functions don't exist when their arguments are negative, so I know x equals negative 4 was an extraneous solution. How about x equals 3? If I check that, I notice that it makes both of the arguments positive. That's good. It means those functions exist. But I should also take the time to make sure it also makes the left side of this equation equal to the right side. So if I sub 3 in, let me just do a quick check. On the left side, I would have log 5 plus log 2. I can combine those together by multiplying their arguments to become log of 5 times 2, which is 10. And log 10 is, of course, equal to 1. Which is what's on the right side of the equation, so 3 is a good solution. Let's do C. This one will be a quick one. It's already in the format where I have a number is equal to a logarithm, so I'm going to convert it to exponential form. 2 to the power of 4 equals the argument. And now this is just a linear equation to solve. 2 to the power of 4 is 16. I'll move this negative 10 to the other side by adding 10 to both sides, and that gives me 26 equals 2x. Divide both sides by 2, I get x equals 13. We should double check this answer. If I sub 13, it makes the argument be positive. It makes it actually be 16. And I know log base 2 of 16 is 4. So x equals 13 is a good answer. Part D, this one, I think what I'm going to do is move this 2 up as the exponent on the argument of the log on the right side. So I have log of x plus 5 equals log of x minus 1 squared. When we have two logs equal to each other, where those logs have the same base, well, they're both the common logarithm, so their base is both 10, I can just set their arguments equal to each other. So I can just set x plus 5 equal to x minus 1 squared. Right? The only way this equation could be true is if the arguments were also equal. And now I have a quadratic to solve, so I will expand the right side. X minus 1 all squared would be x squared minus 2x plus 1. Set the quadratic to 0 by moving all the terms to the right. I'd have x squared minus 3x minus 4. I would then find numbers that have a product of negative 4 and a sum of negative 3. The numbers that work are negative 4 and 1. So I know it factors to x minus 4 times x plus 1. So the solutions are 4 and negative 1. But I have to double check those. Let's make sure neither of those are extraneous. I see that if I subbed my answer of negative 1 into the argument of this logarithm, it makes the argument become negative 2. Log of a negative number does not exist, so I know for sure x equals negative 1 is an extraneous root. How about x equals 4? If I sub it in for this x, it makes this argument be 9. That's fine. If I sub it in for this x, it makes this argument be 3. And I can see that would actually make left side equal right side as well, because I'll show the check. On the left side, I would have log 9, and on the right side, I would have 2 log 3, which I know is equal to log of 3 squared, which is log of 9. So I know x equals 4 is a correct solution. Oh, we actually have 2 more equations to do. Part E, I actually see I can solve this in just a couple steps. I can take that exponent of the argument, which is my unknown x, I can use the power rule and write it as the coefficient of the log right away. So I have 12 equals x log base 2 of 8. I know what log base 2 of 8 is. What exponent goes on 2 to get 8? That's 3. Divide both sides by 3, I get x equals 4. And you could check that in the original equation, and you'll find out that that is the correct answer. F, I will start by writing that 3 as the exponent on that x. And now I can combine those two log expressions. They have the same base, and they're being subtracted, so I can write them as a single log by keeping the base and dividing the arguments. And now I have an x to the 4 divided by an x cubed. So that's equal to log of 2x equals log 2. Now that we have log equal log, where the logs have the same base, we can just set the arguments equal to each other. So I have 2x equals 2, which means x would have to equal 1. And if you check that answer in the original equation by subbing it in for x, you will get left side equals right side. So I know that x equals 1 is a correct answer. So that's the end of that test. If you want an extra challenge, feel free to try and write the product of these three logarithms as a single logarithm. Feel free to leave what you think is the answer in the comments.
Jensen Math!